On Project Pegasus, one of my responsibilities was scattering interesting looking procedural meshes around the terrain. And I wanted a way to do this that got me a little bit more interesting result than just using a Heightfield mask to distribute random points. And while figuring out an approach to do this, I came across something that I find is generally more useful and can be applied to a wide variety of challenges. And that's the concept of advecting points across a volume. So in this case, advecting points using the height gradient and rolling them down the hill can lead to results where you might want to sort of like imagine rocks have fallen down and collected at the bottom of the hills. But you can also roll the points up the hill and produce a similar effect where maybe the outcrops and sort of peaks have been isolated. Beyond that, I realized you could also use this information to create essentially trails of where those paths have been and end up with something that looks an awful lot like the output from the Heightfield flow field node or Heightfield erosion. And not only that, but if we sort of expand our thinking slightly and think, well, we don't only have to roll up and down according to height, we can also roll across the height and extract some interesting looking kind of contours from the terrain, or even up and down according to other masks, such as the ambient occlusion on the terrain. We can use this to produce a very wide variety of interesting, unique, and cool effects, both for scattering meshes and for texturing. So I'm going to dive into the raw vex of how this was set up, and then also explain the way that we've used this inside of Project Pegasus. So to begin with, let's take a look at how advection works in the context of 3D geometry, since Houdini already has some tools that relate to this. Let's throw down a test geometry pig head. We'll then convert that to a VDB from polygons. Why am I struggling so hard to type that? VDB from polygons. There we go. Took me a minute. And what we need to get from this is actually the gradient. So we're going to use VDB analysis. And this is going to give us by default the gradient there. Next up, we'll scatter some points onto the pig head and simply use a node called volume trail, which requires the points in the left input and the velocity volume in the right input. And straight away, we can see that as I adjust the trail length, we get these points moving away from the normal of the mesh. So that is the gradient in this case. If we were to put down a volume wrangle, which allows us to manipulate the volume with vex coding, I'm just going to go ahead and modify that volume, which in this case is called surface. What I want to do is I actually don't want to get the normal here. I actually want to get the cross product of the normal with the up vector so that we have points that kind of slide around the mesh. So first of all, I'm going to set vector up equal to up. And then I'm going to say at surface equals cross at surface and up. V at surface, let's double check. And there you can now see we get another result, which is also interesting. I disable the wrangle, this is what we had originally. And this is once we've done that. So this effect is commonly used to kind of create procedural models of plants growing up or along surfaces. It's also used for a variety of other interesting kind of abstract effects as well. But if we search Advect, we're going to see that native Houdini has a bunch of advection tools, but none that relate to height fields. In fact, the only tool that relates to advection of height fields is one that we've already created for Project Pegasus, which will be available publicly when we release it. But let's have a look at how we set that up from scratch. First of all, I'm going to throw down a height field noise. I'm going to take a look at the result we get from that. Then, because we might as well, we can put down a Heightfield flow field. And we're going to look at what this terrain looks like with kind of the flow lines being isolated and picked out. Why am I doing this? Well, it's to kind of illustrate a point and the direction that we want to head in. If I decrease the number of spread iterations to 0, or maybe 1 is needed at least, we're going to see it's probably quite hard to see, so I'll increase the rain amount. We've got basically a bunch of points that have been scattered on the terrain. And as we increase the iterations here, you can see that they start to develop these kinds of streaks. And the longer we pull that, the longer the streaks get, until we end up with the final result, which is what you can see here, the kind of like the flow fields of that terrain have been generated. And you can kind of imagine this as if we were to go ahead and just scatter some points on the Heightfield and try to roll these points down the hill, we might end up with something similar. So that's what we're going to try to do. On the Heightfield scatter, I'm going to turn off keep incoming terrain, so we're left with just the points. And we're going to put down a node, again, not volume wrangle this time actually, because we want to operate on the points. So we're going to put down a point wrangle, which operates on each individual point from the scatter. And the second input is going to be the Heightfield. Fortunately in Vex, we have a bunch of ways of dealing with and accessing data inside of Heightfields, or volumes in general, because that's what landscapes are in Houdini. They're just 2D volumes. What we're going to do is we're going to put down a node called volume sample, and we want to get the first input because that's the input that contains the volume data. And we want to get the height information at position P, which is the position of the point. Why are we looking for height? Well, that's because that's one of the volumes available to us in the Heightfield, and it's the one which contains the height information. We're going to save that into a float. Float height equals volume sample height. And then what we're going to do is we're going to zero the points in the vertical axis, and then we're going to use this information to snap them back to the position of the Heightfield so that we can verify that this indeed is working. I'm going to put down one more point wrangle. I'm going to call this 0 points. I'm going to call this, we're going to, in this, we're going to type in at p.y equals 0. We can see now that this has now snapped all of those Heightfield points to the ground plane. If we go into the second point wrangle, type at p.y equals height, it now snaps it back up to the height of the terrain. We can see there's no difference between the raw Heightfield scatter and the result we now get from that point wrangle. I'm going to call this point wrangle Advect points along terrain, or Heightfield Advect points. Let's go with that. But we're not interested in just sort of snapping the points to 0 and then snapping them back to their original positions. What we actually want to do is we want to move the points along the Heightfield gradient. So what we can do is we can initialize a vector called gradient, and then we can use command volume gradient to get gradient of height at position P. Okay, so we have the gradient, and what we want to do is we want to say at P plus or equals gradient. And we're going to see, oh, you might, if you blinked, you missed it. You're going to see there's a very slight change in the position of the points. So we want to apply a little scale factor, make that more apparent. Now, as I increase the scale factor, we can see those points are starting to move. But it's a little bit chaotic. And why is that? It's already interesting, but I don't really get the impression that we're kind of moving in the direction of those kind of flow lines that we're aiming for. So why is that? Well, it's because we're sampling the points, the Heightfield's gradient only at the original point position, whereas really we want to take multiple steps and sample the position of the Heightfield, the gradient of the Heightfield at each incremental step. And as we increase the number of steps and shorten the distance between steps, we're effectively increasing the resolution of this kind of simulation. So in order to do this as a kind of incremental process, we need to use a for loop. We can say for int I equals 0. That means start at 0, step 0. We're going to say I is less than steps. So we're going to need to initialize an integer called steps that defines how many steps we're going to take. And we're going to do I++, which simply means we're going to add a 1 to I at every step. Okay, so we've set up our for loop, and we need to initialize steps. I'm going to type chi to make that a variable that we can control on the wrangle itself. Let's set the number of steps to 10 by default. Okay, so we're going to need the sampling of the height and of the gradient to be inside the loop. There we go. It's better practice to initialize the variables once. So I'm just going to do that here. And we can then remove the declaration of the type. Now we need to actually increment these values inside the loop as well. And straight away, you can see we get a result that's much more interesting. I'm going to go ahead and decrease the scale of each step, and I'm going to increase the number of steps to 50. And you can see now what we get is very, very interesting. The original points, in fact, if I just go and edit this parameter interface and change the step slider to encompass a wider range, Now, as I drag this step slider, we can see those points are moving sort of from their original position, or the ground in this case. Sort of one step is required to snap them back to their original location because of this logic where we previously zeroed it. But as I now drag this up, we can see that those points are sliding up the hill, which is very cool. If I wanted them to slide down the hill instead, I would simply need to negate the gradient. So reverse the gradient. We can now see that as I increase that value, we're ending up with something that looks rather similar to the kind of patterns we're getting from the Heightfield flow field. And this is already very useful. We can use this to simulate kind of rockfall and scatter and collection of rocks in sort of logical areas. Wherever they would most likely accumulate is where this is going to allow those rocks to accumulate. And it's actually going to do a more interesting, I think, a much more interesting job, much better job than if we simply used the result flow field and did a scatter natively inside of that. The reason I prefer this is because I need to make sure the mask is hooked up too. But the reason I prefer this is because we get a pretty uniform looking result here, and you can get the density to sort of like drive the density of the mask to drive the density of the points. But with this Heightfield Advect points, it's much more explicit how much you want these points to sort of collect in the crevices. Whoops, what have I done there? I'm just going to go ahead and reload my desktop, restore that to how it was before. So I think this is a more interesting way, and I like that in this case we're starting from a sort of like a basic equal distribution, and we're sort of bullying and pushing and abusing those points around into the way that we want them to behave. And if you wanted to thin them out, it would be as simple as fusing with a threshold. As you can see here, we can use that to sort of decrease the density of points and avoid rocks that might sort of penetrate each other. So yeah, this gives you a lot of options. Which we took advantage of in Pegasus, which I'll talk about later as well. But this is pretty cool. We can now move points up and down, or at least one or the other, depending on what we hard code in the code here. So let's go ahead and make sure that that's something that we can control via parameter. So we're going to say mode is now a parameter, and we're going to go and edit that parameter interface, and we're going to change the type of mode to be a menu. So means 0 is going to be roll down. Whoopsie daisy, make sure that saves. 1 is going to be roll up. And then 2 is going to be one we haven't talked about yet, which is going to be roll across. And this is where we can start to get into the really funky behavior that reveals itself once you're sort of setting this logic up yourself. So we've got roll up, we've got roll down. What does roll across mean? First of all, let's just take advantage of that mode. So this is where we are applying, deciding whether the point should roll up or down the hill. So we're going to say if mode equals 0, we're going to roll with the way that, the default behavior of rocks roll down hills. Whereas if mode equals 1, we're going to get rid of that negation so that it rolls up the hill. As for when mode equals 2, roll across, in this case, it's going to be slightly more involved. So we're going to make a sort of block here underneath the if statement, and we're going to manipulate gradient before we apply it. And gradient is going to become equal to the cross product of the gradient and up, just like we did with the pig head at the start, which means we need to initialize up, like so. And now if we go ahead, choose roll across, it might be very hard to see what's going on, and that's totally normal. We can see some sort of structure starts to present itself, especially as you increase these values to be rather extreme, which gives you an inclination of sort of an inkling of what we're trying to achieve with this setting. This already looks quite cool. But what we can do to make this even more apparent is we can go ahead and add the ability to create trails after each of these points. So the way we're going to do that is, I'm just going to make sure that this is a little bit cleaner first. The way we're going to do that is at the end, I'm going to say if trails equals 1, I'm going to remove point, the current point, like so. And I need to go ahead and make sure that we've initialized trails there. So we're going to say int trails equals chi trails, just like mode. It's kind of another mode in a sense. So we're going to set trails to 1. So now when trails is 1, those points are removed. And we're also going to do something else. So that means that necessitates putting this into a block there. I'm I'm going to remove point, and we're going to go add prim. And we're going to add a prim to the first input itself. I'm going to add a polyline, and we're going to add it to points. But we haven't defined what points is yet. So first off, we need to go ahead, and actually I should really have tidied this up as well. So I'm just going to make sure that the contents of the for loop have been tabbed like so, make it a bit clearer what's going on. And what did I say I was going to do? I was going to initialize an array of points like so, which is currently empty. I'm going to say if trails equals 1 as well, after the point has been moved. If trails equals 1, we're going to add 2 points. Sorry, we're going to add to the points array. We're going to add we're going to add a point at P, the current position, and it's going to be added to the index I of the array points. And now we can see if I decrease the number of steps, decrease the scale a little bit, I've definitely done something wrong. So what's going on here? If trails equals 1, points, add point 0p, we're adding points, so add prim. Okay, we're going to go back and actually set the number of steps to 1, to 2, scale 2. So what's going on here? At P, I see. Okay, so finally we actually need to, yeah, I've messed myself up with my colons there. So not my colon, my braces. So actually this needs to again be set after that final at p.y equals height, because otherwise we're not getting the current height of the landscape. There we go. So now as I increase the number of steps, with the mode roll across, becomes really apparent what that's actually doing. It's producing this really beautiful kind of contouring pattern around the Heightfield, which I absolutely love. And not only that, if we now go ahead and set that to be rolled down, we're going to see we get beautiful flow fields, very similarly looking to the Heightfield flow field that we've got here, and the rolling up as well, which really picks out those kinds of ridge lines and you know, kinds of like well, it's just the inverse of rolling down, I suppose. So this is really nice effect, and what I like to use this for is actually to kind of mask and modify the kind of like incoming terrain. So Houdini doesn't have a mask by points by default. So what we need to do is we need to put down another volume wrangle. This time the volume is going to be the first input on the left there, because we're working on the volume. And it's going to look very similar to the advection by points. So we're going to call this Heightfield mask by points. And in the Heightfield mask by points, we need to get the nearest point to the Heightfield. So we can use int point equals near point 1, because the points are coming from the first input. And again, we use at p to get the nearest point. And then what we want to do is we want to get the position of that point. So we're going to do point 1 p point. So we're getting the position from the first index, from the point coming from the first index that's the nearest so the first index of the wrangle. Then we can go float distance equals distance, the function distance at p compared to pos. So that's the distance from the current part of the Heightfield, from the Heightfield to the point everywhere on the Heightfield. And then we can say f at mask equals distance. And straight away we see something. We're not necessarily seeing what we would expect to see here. I would expect to see that we would have lines kind of like matching roughly where these streaks are. So what's going wrong? Well, this is because actually, when we're talking about volumes in Houdini, we're talking about 2D volumes, which only have an X and a Z coordinate. They do not have an up coordinate or a Y, or the Y vector, which is the up coordinate in Houdini, because the Y is actually represented by height, which is the data stored in the volume itself. So we can just double check that. Go and have a look at Heightfield noise. We have, in fact, just the height here. And that's what encodes essentially what we think of with points as being p.y. Okay, so how do we remedy this? Well, quite simply, we're just going to grab that 0 points. I'm going to wedge it in between the Heightfield Advect points and the Heightfield mask by points. And now we can see that all of those points have been snapped down to 0. which is actually perfect because that's what the volume is expecting to see in regards to its coordinates as well. So we've got the distance, and if we now divide this by some factor, we can sort of change the result we get from that mask. And just to make it a little bit clearer, you can go Heightfield mask blur as well, and maybe just do one step blurring. Sort of gonna make it a little bit clearer, which kind of portions. It's just gonna make it look a bit nicer at the end of the day. That's what it's doing here. Okay, so we can show how this is how we can use those points to kind of create nice looking maps on the terrain. And for example, if I was to go ahead and reduce the number of points quite dramatically, and we're going to see what does that look like when I advect the points. We're going to advect by a few more steps, maybe 200 steps this time. There we go. We're going to get these nice sparse kind of flow lines. It's rolling up. Let's roll down instead. There we go. Heightfield mask by points. Let's increase that distance factor. There we go. We can see we can start to really isolate these regions of the terrain and produce some nice looking masks. And while this doesn't get you anywhere different to where really the Heightfield flow field already gets you, what it does start to unlock is the ability to create some pretty weird and interesting looking masks. If you were to sort of roll across the Heightfield here, you can use it to get some sort of like terracing effects. But not only that, you can also go one step further than this, because we're not limited to advecting according to height. We can actually advect according to any sort of mask that might exist on the terrain. This is where we start to really unlock the potential of this workflow. So we do Heightfield mask by feature. Let's go ahead and generate a mask according to the occlusion of the terrain. I'm just going to go and hit the cogwheel and set that profile, that ramp to round. So we get sort of more extreme whites and reds of the mask. And then we're going to plug the output of that Heightfield mask by feature into the advect points. And then inside of the advect points, we can see we're sampling the gradient of height. We actually don't want to sample the gradient of height anymore. We want to sample the gradient of any arbitrary volume. So we're going to create a string called volume, and we're going to make that a parameter volume, like so. And we're going to set the default volume to be height, which means the behavior won't change. And then rather than hard coding height in there, we're going to use volume. Oh, I've actually done the wrong one. So we can fix that, because we want to make sure this height is actually being used to snap the points back to the height of the terrain. So we want to keep that sampling there. We actually only want to change the volume gradient sample to use volume. So there we go, nothing changed. But if I was to now set this mask, we should see, there we go, I was looking at the wrong thing. So height, nothing changes. If we go to mask, we get something different. All right, but we don't like the result. And why is that? There's nothing really obvious about what's going on here. It just appears a little bit kind of janky and broken. Why is that? Well, let's just think for a second. If we go back to the original Heightfield and look at it here, we can see it's pretty clear that the height range extends between the height range of this entire terrain extends well beyond 0 to 1 values. The terrain itself has a height of let's have a look, 147 units tall. So that means it's basically 147 meters high. So that means the gradient is going to be much stronger between these points here than if it was simply between 0 and 1. In fact, we can visualize that if we go and remap that Heightfield to be between 0 and 1. We can see that the gradient is almost non-existent, impossible to see. So how do we fix this? Well, one way to deal with this is we actually just increase the scale of the the scale of the steps. But this is a really janky and kind of messy way of dealing with that issue. So what's a better way of doing it? Well, we can normalize the gradient that's coming in. And this is going to show that it always just gives us the direction, not just the not the strength of the slope as well. What's wrong with that? Yeah, normalize. There we go. And now if I increase the number of steps, the scale of those steps, I do appear to have done something slightly wrong here. So let's have a little think. What's going on? We'll mask by feature, mask by occlusion. Let's try rolling down, up. Let's try adding a few more points. And I think I see what's happening here. So remember when we had to zero out the points before we were able to sample the height field? Well, it appears that sampling the height seemed to get around whatever was causing this to not work correctly. But now that we've switched to sampling the any arbitrary volume, the fact that we are sampling from the point's current position, which includes its y position, maybe kind of causing this this unintended outcome here. So we can very easily get around this by just making sure that we set at p.y to be equal to 0 before we do any sampling from the volumes. I'm going to go ahead and decrease the number of steps. So that took a long time to compute. And there we go. Okay, now we're starting to see some interesting stuff. I'm going to go put mode back to roll across. And this is what I was after. This beautiful, intricate, kind of Starry Night-esque looking map of not the contours of the terrain, but something that's still, but a kind of a noisy, interesting texture that does stem from the structure of the underlying terrain. Because I kind of have this problem with noise. As I really don't like using it. I like trying to avoid it as much as possible. So finding interesting ways to generate patterns on the terrain that stem from its actual structure and morphology is really interesting to me. And I could imagine using this in a variety of ways to produce, I don't know, like sort of cool looking terrain texturing, cool look terrain effects. Let's have a little look what happens if we use that mask by points. We end up with these kind of swirly, basically looks pretty similar to noise, but we can sort of satisfy ourselves in the knowledge that we didn't use noise, we did something a little bit fancier. And if we were to go and then put a sort of mask blur, mask blur after that mask by feature, you can see how you can dramatically alter the outcome here by just blurring the kind of result of that occlusion, producing what I think is actually really quite a beautiful effect there. So we don't have to limit ourselves to only applying this once as well. We can, of course, grab that Heightfield Advect points, and we can plug those in to the first input, plug the Heightfield into the second input. Because we're producing trails on both, it's going to be causing some slight issues there for performance. But if I now turn off trails and allow these to roll up or roll down, maybe decrease the scale of each step, you can see that we can sort of cause these distort these patterns a little bit according to the terrain as well, sort of taking it even one step further, like so. Quite a small difference between those there, but it's still kind of food for thought and kind of effects you can achieve. Of course, we don't just have to use the occlusion. We could also mask by slope, and you can see how that. You can see how that gives us, actually, in this case, quite a similar looking result. But as we, look at rolling up and down as well, how we can see how this one sort of like is grabbing the peaks and valleys in a way. It's sort of creating radial splays of points according to peaks and valleys, whereas this one's going to creating radial splays of points that sort of center on the slopes there. So yeah, I'm not really sure exactly what you might use this for, but it's certainly a pretty cool tool to have in the arsenal. And as we decrease the amount of coverage of points there, and maybe increase the size of the steps, you can see how you can use this to sort of achieve again some sort of quite nice and different sorts of results there. So yeah, that's basically it. I'm a really big fan of this technique, and I think that. Yeah, it'd be really cool to see what kinds of cool and interesting effects people come up with. On Pegasus, we obviously created our own Heightfield Advect points HDA, which does basically everything we've just talked about and set up. So, so you don't have to go through the setup yourself if you don't want to. What am I doing wrong here? Trails on, yes, there we go. And it's also got some additional kinds of sort of helper features, like the fact that you can actually smooth the gradients of the steps that are being taken, and there's also this kind of prevent overtaking feature, which might not currently work, but hey ho, they will work whenever we ship it, and they do some cool nice things as well. So yeah, that's basically it now. Thanks for your time, and happy Houdiniing.